Hi, my name is Yu-Chen. I'm with the Remote Presence Video team in Meta. We work on improving video quality across the Meta family of apps. Today, I'm going to share our experience using AV1 to improve video quality for RTC at scale. AV1 is getting more and more popular in the video industry. Actually, Apple recently announced AV1 hardware decoder supported on their new devices. So it seems that adopting AV1 is getting more popular and becoming a trend, and this is favorable for RTC. Earlier this year, Nicholas from our team shared some initial results at the RTC at Scale event. Since then, we have hit several milestones and successfully launched AV1 on the Messenger app. There are more than 1 billion monthly active users on Messenger. This is a large scale, and including devices from desktop machine to mobile phones. Today, I'm going to share what we have learned through our development process. For people who may not be familiar with real-time communication or RTC, I'm going to start with a brief intro. The most popular use case of RTC is video calling. Unlike video on demand, the RTC has to deal with end-to-end video latency. Typically, we want to keep end-to-end latency to be less than 300 milliseconds. Once the latency goes over, the user starts to feel a delay. So it's always a struggle for RTC video coding system to provide high quality while maintain the latency low. In this case, we cannot do multipath encoding. The decoder side cannot do much buffering. Any bitrate overshoot would likely introduce a freeze on the code. And the RTC client has to do both real-time encoding and decoding. Both consume a lot of power. So lowering the power is critical, especially on mobile devices. So while we're interested in AV1 on RTC, let me show you some quality comparison between 264 and AV1. Here we enable AV1 on Messenger app and has video call on two iPhones side by side. The bitrate is restricted to 100 kbps. AV1 is on the left, 264 is on the right. By the way, this is Roger, our manager. You can see that the 264 video is blurry and the AV1 video is visually better. This is a good example of the benefit of adopting AV1. We have seen the motivation for adopting AV1 on RTC. In the following slide, I'm going to share what we have learned through our development process. I'm going to share more results of AV1 in the first session. I will talk about the 3 important challenges we faced, including my favorite, which is increasing AV1 call coverage, as well as the solution we came up with. I will then talk about how we measure the impact on the product. Personally, I find this is to be most interesting and most critical. Here are more detailed results of AV1 calls on Messenger app. We have seen quality comparison under 100 kbps at the very beginning. If we further restrict the bitrate to 25 kbps, quality improvement is even more obvious. Low bandwidth network is an important scenario on Messenger app. This is especially true on mobile devices because we have to handle the poor network condition. The fact that AV1 gives very obvious quality improvement at low bitrate makes it a desirable codec for us. We have solved visual comparison. Let's look at the number. These are rate distortion curves. We usually use these to compare the coding efficiency of different codecs. The horizontal axis is bitrate, the vertical axis is PSNR. We encode a video at different bitrate. H264 is lonely rate line. Other lines are different AV1 encoding preset. We use BD rate to measure the difference in comparison efficiency. From the top figure, we can see that under the same quality, AV1 saves about 30% bitrate, and under the same bitrate, AV1 can improve PSNR by 2 dB. Because AV1 offers screen sharing content coding tool support, in screen sharing scenario, the improvement that AV1 can provide is even more significant. We can see evidence in the bottom figure. Last but not least, we also observe improvement on user feedback in the A/B test for AV1 on Messenger. AV1 has several advantages for RTC. First, it offers better coding tool and so better compression efficiency and better video quality. I have shown you data to support this. And AV1 has RTC coding tool which enable encoder to be quickly adapt to the network during a call. This is critical. Two issues are important here: change in network bandwidth and packet loss. In order to handle change in bandwidth, the encoder has to adjust FPS and the resolution during the call. However, a change in resolution usually means that the encoder has to encode a new keyframe. This will introduce a bitrate spike and a video freeze. AV1 provides a new coding tool called Reference Picture Resampling or RPR to solve this problem. This tool allows encoder avoid encoding a new keyframe when resolution changes. Finally, there are several scenarios specific to real-time communication which we have to take care of. Screen sharing is an example. AV1 also comes with screen sharing coding tool support, which can improve user experience. In our experience, parallel mode can effectively improve video quality by preserve sharp edge of text. Also, intra-block copy can significantly reduce screen sharing size. The fact that AV1 provides these two coding tool support as baseline per file is a huge plus. So I have shown the benefit of having AV1 on Messenger. Let's talk about 3 challenges and our solutions. Binary size was our first problem. For example, if we integrate liblm into Messenger, we will see an increase of 1.7 megabytes in binary size or 600 kilobytes after compression. An increase in binary size like this will lead to many issues. Update successful rate will be affected, so users would prefer not to update and keep using outdated version. Application start time would increase, and general software health metrics such as memory usage and crash rate would be affected as well. To give a rough idea, an increase in order of 600 kilobytes is a major problem and could mean a whole year feature budget for a large organization. We have a couple ways to mitigate the problem. First, we can use dynamic download framework to download AV1 as a separate feature component. Usually, this is our first go-to when we integrate a large library. However, the dynamic download framework is not perfect. In our experiment, we do see some download failure, perhaps due to bad network, device issue, or just some random failure. This will definitely affect user experience. So we prefer to reduce binary size instead of relying on dynamic downloading. We could optimize binary size. For example, quantization matrix is a coding tool in liblm. It takes up to 60K, which is about 10% of total library size. With optimization, it can be reduced to 30K. We can even go with the end-to-end pipeline optimization and remove unused coding tool from library. In the QN example, we can completely remove it and save 60K. At the app level, we also have a couple of options for optimization. For example, besides RTC, the app also has other features such as transcoding on video message. We can make some features share the same library to save binary size. Or we can make use of built-in codec support in a device instead of adding new codec library to the app. Our second problem is that AV1 adds significant computing capacity. This is not surprising. Even though the more advanced coding tool can enhance coding efficiency of AV1, it also requires more computing during encoding. The question then is, how this computation increase impact the app? In order to understand the power impact of AV1 computing, we measure the power consumption on a Pixel 7 during the AV1 code. We saw an increase of 0.1 to 0.3 watt when switching to AV1 encoding, which is 4% to 11% power increase. In addition to power consumption, memory usage increase is another issue. We observe a large memory usage increase on AV1 encoding compared with 264. This results in app crash regression, which I will explain in more details later. Since AV1 code needs more computing resources, the first thing we have to do is to identify the list of devices capable of using AV1. We don't want to cause video freeze or overheating when AV1 is mistakenly enabled on the ineligible devices. Having a list of eligible iPhone models was easy because there aren't many iPhone models. For Android device, it's more challenging. It's just too many legacy Android devices. We try selecting device by memory, the year of release, and even the Android OS version. However, none of these strategies are reliable. In the end, we use Meta in-house device benchmarking system, and we are able to have a reliable list of Android devices. Our problem didn't stop there. We observed another issue from the A/B test, out-of-memory crashes. Initially, we suspect there may be memory leak in AV1 library, which was not the case after some investigation. There may be other background app causing the leak. However, with high memory usage, there is higher chance of running out of memory and triggering the crash. Memory usage increase is correlated to video resolution. So, to mitigate the regression, we design a codec switch mechanism. The AV1 is initially enabled only for low and medium resolution, and is fallback to 264 for high resolution. In fact, generally, hardware codec is preferred for high resolution because of power consumption. So, before AV1 hardware codec support become available, we believe that is good strategy not to use AV1 for high resolution on mobile devices. So now we have solution for binary size, power consumption, and memory usage. We got positive result from the A/B test. We successfully launched AV1 on Messenger and make it available for high-end devices. On Messenger, we are covering about 60% iPhone models. For Android, however, the coverage is much less, at 15%. I will explain why. Even though we now have a list of all high-end Android devices, we found that a lot of factors could reduce the computing capability of these phones during a code. For example, if an app consumes a lot of power and running in the background causing device overheating, the device would have to reduce CPU frequency. To better understand the issue, this is the encoding latency based on the data we collected from the messenger. The distribution representing AV1 is more on the right, indicating higher latency compared with 264. We already expect that. What was surprising was that the latency of some device was really close to the input frame rate. This means that this device is almost unable to do proper real-time encoding. In fact, in this case, this device would become hot and cannot encode AV1 video in real time. This results in video freeze. As a solution, we had to make our Codex Selection smarter. Besides resolution, we have to consider some device health measurement, such as encoding latency and even device battery level, to determine whether the device has enough computing power and whether it has to fall back to 264. With a more reliable Codex Selection strategy, we are able to increase Android device coverage by making AV1 available to mid-end devices. Some of these mid-end devices are not able to do real-time encoding, but they are able to do real-time decoding. In this case, we can use a symmetric codec design. VN devices would still encode and send 260 video, but they are receiving AV1 from the high-end device on the peer side. The way we have effective increase in AV1 coverage on Android devices. In an effort to continue improving code quality, we are working on this topic, encoding preset, rate control, and resolution tuning, and it's always worthwhile to improving encoding algorithms for quality improvement. When we ship a feature, how could we measure the impact become an important question. The measurement strategy has to not only provide evidence that the feature comes with many benefits, but also monitor the impact of feature in long term. So we need an in-product quality measurement. Currently, there's not a reliable quality measurement in the RTC pipeline. We simply don't have a good solution for this in the industry right now. I will use the WebRTC as an example. Its report resolution and the compression level, which is QP. This is more of a quality approximate. But if we want to compare two different codecs under the same code condition, in our case AV1 versus 264, QP doesn't work. This is because different codec has different quantization definition, not to mention that each codec also has its own in-loop filter design. So we have to design our own quality measurement. It has to be low complexity so that it can cover all kinds of devices. In the field of video, PSNR is generally regarded as a reliable quality measurement. It does not require a lot of computing, but we have challenging if we want to implement the computation of PSNR in RTC pipeline. First, PSNR is a full reference matrix. However, in RTC video pipeline, the sender does not have decoded video. The receiver does not have original video. In other words, we cannot compute PSNR. Moreover, before encoding a video, a sender will scale the video according to bandwidth. This makes PSNR computation more challenging. To overcome these problems, we propose a framework for PSNR computation. We first modify the encoder, making the encoder report distortion caused by compression. Then we design a lightweight scaling distortion estimation algorithm. Based on the distortion value reported by encoder and the algorithm, a PSNR value is computed. With this system in place, now we could reliably measure the impact of AV1. There are more details to the design. For example, we observe a correlation between scaling distortion and encoding distortion, and we have to modify our algorithm accordingly. We are summarizing our findings and work, and will be submitting these to academic conferences. To sum up, we believe this is the right industry moment to adopt AV1 in RTC. In-product quality measurement is still a challenging issue in RTC product. We are looking forward to industry collaboration on this topic. Adopting AV1 also creates opportunity for metaverse applications. Some lessons we have learned could be potentially helpful to AV2. Finally, as we continue to improve AV1 code quality, an interesting direction is to use machine learning to solve some issue we encountering. This marks the end of my presentation. Thank you for your attention.